Welcome to the Layout Math tutorial. My name is Catherine Triggett. I'll be your instructor for this tutorial. As a Red Seal journeyman carpenter and as an instructor for over 10 years, my experience has taught me that math isn't everything we do on the job. Every time we use a tape measure, we're using math. Every time we mark 2 points and snap a line, we're using math. Math is an integral part of layout. With a good working knowledge of the math we'll review in this tutorial, you'll be successful in tackling the most challenging layout jobs. Math can be intimidating to many, and it can be a barrier to successful training. But that's why we're here. We're going to make this easy. I want to congratulate you on your dedication and commitment to training and improving your skills. I know from my experience, continual skills training leads to greater employability and production on a job site. And this ensures future work for Local 27 carpenters and keeping the UBC strong and competitive. So let's get going. Today we're going to go through our conversion lesson. So we're going to convert from feet, inches, and fractions of an inch to decimal feet. When we're out in the field, we often have to do different calculations. When we're working with Imperial, we need to be able to do calculations together. So we convert from our 3 units of feet, inches, and fractions of an inch to decimal feet to be able to do our calculations with. Okay, so I'm going to do a conversion on the board from feet, inches, and fractions of an inch to decimal feet. And then we're going to convert it back again from decimal feet to feet, inches, and fractions of an inch. So we're going to pick a number to start our conversion with. So we'll start a number like 7 feet, 4 3/4 of an inch. Our end goal here is to be able to convert this from 3 separate units of measurement into 1 unit of measurement, being decimal feet. Whenever we're doing our conversions, we're going to start with our smallest unit of measurement first. In this case, it's going to be 3/4 of an inch. Most of you are going to understand that 3/4 of an inch is 0.75. To be able to actually do that calculation, we're doing 3 divided by 4, and that's going to give us our 0.75. This is now in decimal inches, so we can put the unit of decimal inches on this 0.75. From here, then we can add our 4 whole inches into this equation. So we take our 0.75 and we add our 4 inches. And you can do this with your calculator alongside me on the board here. So now we're at 0.75 decimal inches. To go from 0.75 decimal inches into decimal feet, we then need to convert this to decimal feet by dividing this by 12. So we take our 4.75 and we divide that by 12, and that's going to give us our decimal feet. And you can punch the numbers in on your calculator alongside me. 4.75 divided by 12, and that's going to give us 0.39583 repeating. That's our conversion. We can add this number now back to our whole feet, and then that's what we're going to have as our answer. It's going to be 7.39583, and this symbol up here is standing for repeating decimal feet. This number here is equivalent to this number here. They are equal in value, just represented in a different unit of measurement, from feet, inches, and fractions of an inch, down to decimal feet. So now what we're going to do is we're going to go from decimal feet back to feet, inches, and fractions of an inch. We're going to pick a new number to start with here, and let's go with 13.7968 decimal feet. So now that we've done our calculation and come up with this number, we need to actually convert this back to a number that we can read on our tape measure. So we're going to go from decimal feet to feet, inches, and fractions of an inch. Our 13 feet, that's not going to change. So we can put that in our answer right away. We're going to start with the fraction or the decimal feet that we have here. So we're going to start with 0.7968 decimal feet. We need to convert this back to decimal inches. To go back to decimal inches, we're doing the reverse as we did before. We're now going to multiply this by 12. Okay, so follow along with me on your calculators. 0.7968 68 times 12, and that's going to give us 9.5616. This is now in decimal inches. So what this is telling me is that we have 9 whole inches. So I can subtract the 9 out of my calculator and put that right away into my answer. So I know I have 13 foot 9. Now we're going to figure out our fraction of an inch. So I'm going to subtract this 9 out of here and just deal with my 0.5616. Now generally we have to have a conversation about tolerances. In most applications in construction, if we're within a 1/16 of a degree accuracy, we're pretty good. So we're going to say that as long as we're within a 1/16 of a degree, we can go. So that will be our conversion here. We're going to multiply this by 16, and that's going to give us our fraction of an inch. So again, follow along with me on your calculators. We subtracted the 9, now we're left with just the decimal, and we're going to multiply that 0.5616 by 16. And what we come up with is 8.985/16. What this is telling me is this is actually 8.9/16. So here we're going to have to actually round this up. My closest 16th is going to be 10/16. So at that point, I need to reduce that fraction down to its lowest terms. So my answer is going to be 13 foot 9 5/8 of an inch. We're going to go from decimal feet back to feet, inches, and fractions of an inch so that we can actually read this on our tape measure. We have our 24 whole feet. That's not going to change, so we can put that over on the side as part of our answer. 24 feet. We're going to deal with our decimal of a foot, and we're going to convert that to decimal inches. So we have our 24 whole feet. That's not going to change. Now we're going to deal with this, changing it over to inches. So we're going to take our 0.7968, and we're going to multiply this by 12, just the opposite of what we did in our last one. Okay, go ahead and punch it in your calculator with me. 0.7968 times 12, and we come up with 9.5616. That's telling me that I have 9 whole inches. So I can take that 9 and put it right away in my answer with my 24 feet. Okay? In your calculators, you're going to subtract this 9. Okay, so go ahead and subtract that 9 in your calculator, and now you're just left with your decimal of 0.5616. Now we're going to change this to our fraction of an inch. In most applications in construction, within a 1/16 of an inch is going to be acceptable. So that's what we're going to use here to be able to convert this over to our fraction of an inch. We're going to multiply this by 16. Go ahead with your calculators with your 0.5616 times 16. And here we come up with 8.9856. This is now a 1/16 of an inch. So once we get up with our 8.9856 16ths, we look at our number to the right of the decimal. It's 5 or higher, so that's letting me know that this number is going to round up. So my answer then is going to be 9/16, and I can take this over and put it in my answer. So 24.7968 feet is equivalent to 24 foot 9 and 9/16 of an inch. Okay, so now we're going to go over Pythagorean theorem, commonly referred to on a construction site as 3, 4, 5. Pythagoras' theorem is a squared plus b squared equals c squared, commonly referred to as 3, 4, 5 on a job site. This is all based off of our right angle triangle. A squared plus b squared will equal c squared. You'll see it written out like this. We have 2 pieces of information and we're seeking a third piece. This formula could be adapted depending on the information that we're looking for. Maybe we have C and B and we're looking for A. Or maybe we have C and A and we're looking for B. So the alternatives to a squared plus b squared equals c squared are c squared minus b squared equals a squared, or c squared minus a squared equals b squared, depending on the information that we're seeking. Let's go ahead and do an example together and see how the formula works. So let's go ahead and prove our 3, 4, 5. So let's use 3 feet here, 4 feet here, and we can predict that our answer is going to be 5 feet. Let's go ahead and work the formula together. A squared plus b squared equaling c squared. So we're going to punch our numbers in. 3 squared plus 4 squared equals c squared. We're going to go ahead and square this together. So you'll see a button on your calculator. That is an x to the power of 2. That's going to square the number for us. So go ahead and do it with me on your calculator. 3 squared equals, we get 9. We're going to add that to 4 squared. Remember, it's 4 times 4. By hitting that square button, it does it automatically for us. There's our 16 equals c squared. We're going to add these two numbers together, and then we're going to write down our next steps. So 16 plus 9 is going to be 25 equals c squared. Now, a lot of people think that this is the end of the equation. We have to remove this number. To be able to do that, we're square rooting our 25. Again, you're going to have this button on your calculator. It'll look kind of like an upside down hockey stick. Okay, so once your number 25 is there, you're going to square root that, and you're going to come up with 5 as your answer. And that's how we're proving that 3, 4, 5. If we measure 3 feet this way, 4 feet this way, where 5 feet hits both those parts, that's going to be our perfect right angle. So now that we've done one example, let's combine what we've learned together. So let's do a conversion as well as solving for 3, 4, 5. Let's say we have a building, and we know the diagonal distance of this building is 56 feet, 7 5/8 of an inch. And we know that our other length over here is going to be 36 feet, 9 5/16. We're trying to figure out what this one is here. So we're going to combine two lessons so far. We're going to combine our conversions as well as our a squared plus b squared to equal c squared to solve for this equation. First, we're going to start by converting this. Just like we talked about before, it's going to be starting with our fraction of an inch first, moving to our inches, creating it to be decimal feet. In our calculators, we're going to start with 5 divided by 8. That tells us we have 0.625. So let's do that together. 5 divided by 8 is 0.625. Then we're going to add our whole inches to that number. In your calculator, join in with me and add 7 to that. 7.625. Now to change this over to decimal feet, we divide this number by 12. Divide by 12. Go ahead and punch that into your calculator. You're going to come up with 0.63541 repeating decimal feet. So once we come up with our 0.635416, all we have to do now is add that to our whole feet to come up with our answer. So our answer is going to be 56.635416, repeating decimal feet. Once we finish this one, we can move on to our next number. We're going to now convert our 36 feet, 9 5/16 to a decimal of a foot. Just like we did before, we start with our fraction of an inch first. 5 divided by 16. Go ahead and punch that into your calculators. 5 divided by 16. We get 0.3125. Then we're going to add our whole inches to that. So we're going to add 9 whole inches, 9.3125. And then our last step to convert it over is going to be divide by 12. we come up with 0.7760416 repeating. We add that number back to our whole feet, and there's our answer, 36.7760416 repeating decimal feet. Now that we've converted both of our numbers, we can now use our formula of a squared plus b squared to solve for c squared. So we're going to adapt our formula based on the information that we have here. We're given our hypotenuse already. We're given a vertical. We're trying to seek this information. So let's start by labeling this triangle with what we have. This is going to be c squared. This is going to be our b, and this is going to be our a. Okay, so let's write our formula that we're going to use, which is going to be c squared minus b squared to equal a squared. So we're going to put our numbers into the formula. We're going to do our 56.6354, and we're just going to keep 4 decimal places. We're going to keep our accuracy if we keep 4 decimal places. That's going to be squared minus our next number, which is going to be 36.776 squared, and that's going to equal a squared. Okay, just like we did before, we're going to punch this number into our calculator, and we're going to hit that square button. So we're going to do 56.6354, and we're going to square that number. We come up with 3,207.5685, and I'm going to keep this at 4 decimal places for all of our answers. We're going to subtract that from this number. We're going to pop this one into our calculator next. So our 36.776, and we're going to square that number. And we come up with 1,352.4741. And that's still going to equal a squared. Now we can subtract these two numbers. Our 3,207.5685 minus 1,352.4741. Here we come up with 1,855.0944, and this equals a squared. Remember, to get rid of this square number, we actually need to square root this number. Okay, go ahead and hit that on your calculators, and then you're going to come up with 43.0708, and that's going to be feet, and that's what a equals. Now, we can't read that on our tape measures, so we actually need to be able to convert this number back again to feet, inches, and fractions of an inch, combining all of our skills together. So let's go ahead and do that now. Our 43 feet, that's not going to change, so we can go ahead and put that in our answer right over here. 43 feet. We're going to deal with the decimal here. So we're going to take our 0.0708, and we're going to multiply that by 12 to figure out how many whole inches, if any, we're going to have. And we come up with 0, actually. So we're going to have 0 whole inches in that equation. Okay? Now we need to figure out what our decimal, or what our fraction of an inch is going to be. So we're going to multiply this just like we did before by a 16th. And it tells us that we come up with 13.59 and a bunch of other decimals, which we don't really need to know. What we're looking at is this 0.5 here. That's telling us that it's going to round up to 14/16. Okay, which we're going to then reduce down to its lowest terms and be 7/8. So our missing dimension over here for A is going to be 43 feet, 7/8 of an inch. Here we've combined in multiple skills. We've combined our conversions as well as 3, 4, 5 to solve for this equation. In layout, angles are measured in degrees, minutes, and seconds. As we know from working with circular shapes, there are 360 degrees in a circle. Many layout challenges require us to solve for an angle that is not measured in full degrees. There are 60 minutes in 1 degree, and there are 60 seconds in 1 minute. When we do the math, we realize that there are 3,600 seconds in 1 degree. While this level of accuracy is not realistic, we will encounter challenges where we'll need to add or subtract degrees, minutes, and seconds, or convert degrees, minutes, and seconds to decimal degrees. Let's begin with adding and subtracting degrees, minutes, and seconds. So there are 360 degrees in a circle. In 1 degree, we have 60 minutes, and in 1 minute, we have 60 seconds. So let's take a look at that. 360 degrees in a circle. 1 degree has 60 minutes. We write that symbol the same way we write our feet symbol, but in this instance, this is going to represent for a minute. In 1 minute, we have 60 seconds. So now we're going to add some numbers together. We're going to start with 45 degrees. We're going to go with 35 minutes, and we're going to go with 15 seconds. And we're going to add that to 135 degrees. We're going to add 40 minutes and 44 seconds. And we're going to add these numbers together. When we do this, we're going to start with our smallest unit of measurement, being our seconds. Then we're going to move on to our minutes, and then we're going to move on to our degrees. We're going to start by adding these together, and we come up with 59 seconds. We're going to move over to these units, and we're going to add them together, and you'll notice we come up with 75. We're going to carry this number over at the end of the equation. So then we're going to add our last ones together, and we come up with 180 degrees. Now, we're not finished this equation. Notice how this number is higher than our 60 minutes over here. So we need to carry over our balance. So now that's going to tell us that we have 181 degrees. Our leftover here is going to be 15 minutes and 59 seconds. So when we add those two numbers together, we get 181 degrees, 15 minutes, and 59 seconds. Now that we've added degrees, minutes, and seconds, we're going to subtract degrees, minutes, and seconds. So let's go ahead with our next equation. We're going to start with 120 degrees, 58 minutes, and we're going to use 39 seconds. We're going to subtract that from 88 degrees, 28 minutes, and from 14 seconds. Just like we did on our adding, we're going to start with our seconds, then we're going to move on to our minutes, and then we're going to finish off with our degrees. So we're going to subtract these numbers, ending up with 25. Then we're going to subtract these guys here. We're going to end up with 30. And then we're going to subtract our last one over here, and we're going to end up with 32. So here we have 32 degrees, 30 minutes, and 25 seconds. Here's our subtracting of degrees, minutes, and seconds, and here's our adding of degrees, minutes, and seconds. We're going to move on to converting degrees, minutes, and seconds to decimal degrees. Let's pick our degrees, minutes, and seconds that we're going to convert over to decimal degrees. So how about we start with 28 degrees, 34 minutes, and 15 seconds. Just like we've done in previous lessons, we've always started with our smallest unit of measurement first. So let's start with 15 seconds. We're going to convert this by using that multiple of 60. So we're going to take 15 seconds and we're going to divide that by 60. Go ahead and grab your calculators and start the equation with me. 15 divided by 60 gives us 0.25. Now we're going to add our whole minutes to this equation. So we're going to add 34 minutes to this number. In your calculators, go ahead and add that 34. Then we're going to take our final step, getting this over to degrees. So we're going to do our 34.25 and we're going to divide this by 60. And we come up with 0.57083 repeating, this is now decimal degrees. So we can add this number to our initial amount of degrees, 28, and come up with our answer of 28.5708 degrees. Now we're going to take the number and we're going to convert it back. So we're going to go from decimal degrees back to degrees, minutes, and seconds again. So let's come up with a new number to start with, and we'll show you how to convert back again. Let's say that we have 35.9435 degrees. And our goal here is to convert this to degrees, minutes, and seconds. Just like before, we're basically doing the reverse operation. So our 35 is not going to change. We can leave that as 35 degrees. We're going to start with our decimal and convert to get our minutes. So we're going to put into our calculator 0.9435, and we're going to multiply that by 60 to find out how many minutes we have. Go ahead and punch that into your calculator with me. And we come up with 56.61. That's telling us how many whole minutes we have. We can take that and pop that right into our answer again. 56 whole minutes. Okay? From this stage, we're going to subtract away that 56, leaving us with just the decimal to get how many seconds we have. Then, just like before, we're going to multiply this number by 60 to figure out our total seconds. So go ahead and punch it in your calculator if you haven't already. Subtract your 56 and then multiply that by 60. And we end up with 36.6. So what we can do here is we're going to round our number up to the nearest whole second. So in this case, it's going to end up being 37 seconds. Okay? So our equivalent is 35.9435 decimal degrees is equivalent to 35 degrees, 56 minutes, and 37 seconds. So now that I've worked through one of these equations with you, we're going to take the time to practice this new skill. I'm going to put up some examples on the board. I want you to take this opportunity to pause the video once I've put the examples on the board to work through it on your own. Once you've worked through the examples on your own, I want you to resume the video to be able to see the completion of these problems. Let's start with one going from degrees, minutes, and seconds to decimal degrees, and we'll do another one going from decimal degrees to degrees, minutes, and seconds. Let's start here. Let's say we have 42.9634 decimal degrees, and we want to convert this to degrees, minutes, and seconds. And then let's say that we have 9 degrees, 58 minutes, and 17 seconds. And we want to convert that one to degrees, minutes, and seconds. Go ahead and pause the video now, and I'll see you on the other side. Now that you've had a minute to work through both of these examples, let's go through them together to check our work. Let's start with our decimal degrees, and let's convert this back to degrees, minutes, and seconds. So you probably took your decimal, and you multiplied that by 60 to figure out how many minutes you have. Let's punch it together. And we come up with 57.81. So that tells me I have 57 minutes. So we can go ahead and write our answer. Let's put it down here. 42 degrees, 57 minutes. Let's find out how many seconds we have. We remove that 57, and we're left with just our decimal. And then we multiply that one by 60 as well. And we are left with 48.6. Just like we did before, we have to look at that decimal to know whether we're rounding up this number. So this guy is going to end up with 49 seconds. So decimal degrees, 42.9634 decimal degrees ends up at 42 degrees, 57 minutes, and 49 seconds. Let's go ahead and work through the next one. We started with 9 degrees, 58 minutes, and 17 seconds. Let's convert this over to decimal degrees. We start with our 17, and we divide that by 60. And we end up with 0.283 repeating. Then we're going to add our minutes to the equation. So here we're going to add 58. And we end up with 58.283 repeating. I'm going to add my 58 in my calculator here. And then we're going to divide this by 60. And there's our total. We get 0.97138 repeating. We're going to add this to our 9 whole degrees to get our answer. So when you solve for these equations, we ended up with 9.97138 decimal degrees from 9 degrees, 58 minutes, and 17 seconds. As carpenters, we're sometimes tasked with calculating or determining slope. A slope is defined as the distance in rise or fall from level. An example of this would be determining the elevation for the top of the driveway from the street level. If we know the elevation at the street, the percentage in grade or slope, and the distance to the top of the driveway, we can calculate the unknown elevation. So we're going to work through a slope equation together. We're going to use the scenario that we have 100 meters. This is going to be our elevation at our street level. We're going to say that our driveway is 60 meters. We're going to add a 3% slope to this. And we're going to try and find out what our new elevation is at the top of this driveway. To be able to solve for this equation, we take our 60 meters of the length of our driveway. We multiply this by our 3%. When we multiply our percent, we change our percent to a decimal. To be able to do this, we divide by 100. So we're just moving the decimal 2 places over. So it becomes 0.03. We're going to punch this together in our calculators. 60 times 0.03, and we come up with 1.8. That's telling us the distance from here to here. So all we have to do now is add our 1.8 meters to our 100 meter benchmark to get our new elevation. We add those 2 numbers together, and our new elevation is 101.8 meters at the top of the driveway. A common layout challenge is an arch or a circular shape. To be successful, we must first understand radius, the diameter, and circumference. Once we understand the geometry and math, it'll become much easier to tackle the layout of circular shapes and arches. So we're going to start by just drawing a full circle on the board, right? And our circle has 360 degrees in it. Then we'll talk about the parts of the circle. So if this is the center of our circle, the line coming from the center of the circle to the outside is called the radius. This is exactly half of the center of from the center of the circle to the outside. Then we have the diameter. The diameter of the circle is double the radius. So it goes through the center of the circle and touches the circle on both sides. This is always the longest side within a circle. Then we have the circumference of the circle. The circumference goes all the way around. It's the perimeter around the outside of the circle. Okay, let's talk now about the formula for circumference of a circle. It's going to be pi times diameter to equal circumference. Let's get our calculators out and we're going to go through a calculation for circumference of a circle. So for this, we're going to need to know to use our pi button on our calculator. So you're going to see a button that looks like this. This is going to signify for our pi button. Then we're going to have to be given the diameter of our circle. So then we're going to say that the diameter of our circle is going to be 3 foot 4 5/8 of an inch. So here we have to do our conversions. We have to convert this to decimal feet, right? We did this in an earlier video. So go ahead and convert this number. We're going to start by doing 5 divided by 8 to get our decimal of 0.625. Then we're going to add our 4 whole inches to that and then divide that by 12, getting our conversion of 3.3854 decimal feet. So we can punch that number now into our calculation. So it's going to be pi times 3.3854, and that is going to equal our circumference. So go ahead and hit the buttons with me now. Pi times 3.3854 equals, and now that's going to say 10.6355 feet. Okay, so now that we've come up with our circumference, we're going to convert this back so it's a number we can actually read on our tape measures. So we delete that 10 out of the equation, we take our decimal of 0.6355, we multiply that by 12 to tell us how many whole inches we have. So that's going to say that we have 7 inches. Take away the 7, multiply that last decimal by 16 to get our fraction of an inch. And there we have our last fraction. So our answer is going to be 10 foot 7 and 5/8 of an inch is the circumference of this circle. Now I'm going to go through area of a circle. Our formula for area of a circle is going to be pi r squared. Pi r squared. R stands for radius. Okay? So we need to know the radius of this circle. So we'll say that the radius of this circle is going to be 2 foot 3 and 5/16. So we first need to convert this over to decimal feet again. So just like we did before, we're going to start with our fraction of an inch. So grab your calculators. 5 divided by 16 to get our fraction handled. We're going to add the 3 whole inches to that, divide by 12, and we get our 2.276 decimal feet. Now we can plug that number into our formula for area of a circle. Pi times the radius of 2.276 squared. Okay, let's go ahead and punch this in. You're going to find your pi button on your calculator, multiply by 2.276, and then you're going to need to find your square button. If you're not sure, it's going to look like this. Okay, and you're going to go ahead and hit that button, and there's our equals of 16.274, and now this is in square feet. So there's our answer, 16.274 square feet. And now we're going to transition into segmented arch. So this is another common challenge that we face out on the job sites. On a smaller scale, we can lay this out geometrically. On a larger scale, we do this with instruments. So today I'm going to show you how to do it geometrically. So let's start by clearing this off the board. When we lay out a segmented arch, there's some important information that either we need to have or needs to be given to us. So we're going to refer to something called the chord, which can also be referred to as the span within the circle, and then the rise from that chord to the top of that circle. Okay? So those are the 2 pieces of information that would need to be provided to us. Chord and rise. The chord, we're going to say, is 5 feet. And we'll say that the rise on this case is going to be 18 inches. So we're going to start by laying out that 5-foot chord. Okay? This can be done on the floor by snapping a chalk line. We're going to do it here on the board with this ruler. I'm going to measure out my 5-foot distance. In this case, I'll label it just so it's clear. AB between this distance is 5 feet. Then I'm going to bisect this line. To bisect a line means to cut it in half. Okay? To be able to do that, I'm using a compass. Okay? This can be used as your tape measure on a job site. I'm going to put my compass or your tape measure on your first point, I'm going to pick any number as long as it's larger than half the distance of this line. So in our case, as long as it's larger than 2.5, we're good. I'm going to arc above, and I'm going to arc below. I'm going to do the same thing from B without changing the distance of my compass. Arc above, arc below. Those have created 2 points, calling our intersection points. And we have bisected that line, creating half. Once we have exactly half, now we can use the information of our rise and measure up to what that dimension is. Here we're saying it's going to be 18 inches. So we're going to measure from our baseline up to our rise of 18 inches. Then we're going to bisect that distance. Okay? If it helps, sometimes you can actually visualize it as a line. Okay, so we can bisect this distance. So we're going to do the same thing we just did with our AB line. We're going to now use this point up here to bisect. I'm going to put the point of my compass here, setting it to any measurement as long as it's greater than half the distance of that line. I'm going to arc above, right, from both sides. And then I'm going to do the same thing on the other side. I'm going to make it a little bit bigger so it projects my arcs to the opposite side, which is just going to give me some greater accuracy. Okay. We're going to draw that line in, making sure it goes right through our intersection points. Now, what we have is what we're looking for is this guy right here. This is called our radius point. This is actually the center of the circle. So now that we've found that, we can set our compass on that center point and set it to the distance of A, or our top elevation, or B. It should all be the same. And then we're going to spin to get our segmented arch. And that's how we lay out a segmented arch using geometry. Now we're going to talk about trigonometry. Our first step is going to always be to label out the triangle first. So that's where we're going to start today. So we're going to draw a right angle triangle. And there are 3 pieces that we're going to label out here. Our hypotenuse, which is always going to be the same. The hypotenuse is always the longest side of a right angle triangle. So it's the side directly opposite that 90 degrees, or the longest side in a right angle triangle. Now, your adjacent and your opposite are the 2 other sides that we need to label. These are going to change depending on your angle of interest. So for instance, if we say our angle of interest is going to be this corner right here, that means that we're going to label this side as the opposite. If this side is the opposite, then this side is going to be the adjacent. It is adjacent to the angle of interest. Remember, our adjacent and our opposite can change. It's all based off of that angle of interest. So in this case, our angle of interest is here, so that tells us that this is our adjacent and that this is our opposite. But if our angle of interest were to change and say become over here, then this becomes the opposite and this becomes adjacent. So when we're labeling that triangle, our hypotenuse stays the same, the longest side of our right angle triangle, or the side directly opposite our 90, but the opposite and adjacent are all going to be based off of where our angle of interest is in that right angle triangle. Your angle of interest can be provided to you on a blueprint, or you're going to be turning that angle using a theodolite. The theodolite is another layout instrument which we turn angles with. Now that we've learned how to label the triangle correctly, now we can go through the 3 formulas that we're going to be using for trigonometry. Our first one is the sine of the angle equals the opposite over the hypotenuse. Our next one is going to be ka, which is going to be the cosine equals the adjacent over the hypotenuse. And then our last one is TOA. That's going to be the tan equals the opposite over the adjacent. So now let's work through one of these equations together. So I'm going to start by setting up an equation with our right angle triangle. We're going to be told that this is 15 feet high and that our angle of interest, which is going to be right here, is 47 degrees. So our first step, remember, is always going to be labeling this triangle out. So we can always start with our hypotenuse. That's always usually the easiest side. So if you remember, it's directly opposite that 90 degrees, or it's the longest side of our triangle. From there, we need to put our opposite and our adjacent. Remember, opposite is always going to be the side opposite the angle of interest. So in this case, this is our angle of interest, so our opposite is going to be over here. Adjacent is going to be next to our angle of interest. So now that we've labeled out this triangle, we can now figure out which of the three formulas we're going to be able to use to solve for it if we're looking for the opposite. Okay? And again, depending on which piece of information you're looking for, it's going to tell you which formula you're going to choose. So because I'm given my adjacent and I'm looking for my opposite, I need to look through my three formulas and see which one has those two in it. Okay, so we're looking for the formula that has adjacent and opposite inside. Opposite and hypotenuse, adjacent and hypotenuse, opposite and adjacent. So this will be the formula that we're going to be able to use to solve this equation. So what it's going to look like if we write it out is going to be the tan of angle 47 equals the opposite over the adjacent. Okay, so when we actually work this equation out, what we're going to punch into our calculator is going to be hitting that tan button on your scientific calculator. Tan of 47 times 15, that's going to equal our opposite. So go ahead and hit those buttons with me now. Tan of 47 times 15 equals 16.0855. Let's cut the decimal off there. So that tells us that our opposite is 16.0855 decimal feet long. Okay, now that we've worked through one equation, let's try it again. This time we're going to end up using one of the other formulas. So let's go ahead by start by having our triangle, and we'll set up the information that's being given to you. So our angle of interest, in this case, is going to be 71 degrees. We're told that this is going to be 96 inches, and we're looking for our hypotenuse. We're looking for this side. So let's label the rest of the triangle like we've started before. Our angle of interest is here, so that means our opposite is going to be the side directly opposite that angle of interest. And then the side next to it is going to be our adjacent. So we have our adjacent, and we're looking for our hypotenuse. So now we have to go back to our three formulas and see which one has these two pieces in it. Our adjacent and our opposite, or our adjacent and our hypotenuse. So our sine has opposite and hypotenuse. Oh, look, our cosine has adjacent and hypotenuse. So this is going to be the formula we're going to use to solve. So our cosine of 71 degrees is going to equal our adjacent, which is 96, over our hypotenuse. Okay? So to be able to solve for this one, we're going to say it's 96 divided by the cosine of 71 degrees. Let's go ahead and punch this together into our calculators. 96 divided by, press that cosine button of 71, and we're going to come up with 294.86, and we'll just say 91 inches. So you can see how it's all based off of labeling that triangle correctly. That's really the key and the first step to doing any trigonometry problem. The next concept that we need to review is benchmark, also backside, height of instrument, and foresight. With a firm grasp of these concepts, we can shoot elevations such as footings, floors, walls, caissons, piles, and other building components. A benchmark is a given point of elevation from which all other building elevations are shot. It can be a true elevation based on distance above sea level. Generally, the benchmark is set by a survey team before construction begins. It could be a nail set in a concrete sidewalk, a point on the side of an adjacent building, or even a stake driven into the ground. From this established point, we can shoot all the elevations of the construction project. So we're given a benchmark in the form of a stake in the ground, and clearly marked in the corner of the site for protection, and given a benchmark of 99.00 decimal feet. When I set up my instrument and level it, I can then swing my instrument to my benchmark and shoot my first elevation. From the benchmark to the crosshairs on the instrument, the difference measures 5.58 decimal feet. We then take the known benchmark of 99.00 decimal feet, and then we add our 5.58 decimal feet together to get our total height of instrument. So now we're going to punch it into our calculators. We're going to put in our 99.00 plus our 5.58, and we come up with a height of instrument of 104.58 decimal feet. If we are then tasked with setting the top of elevation at a footing form, for example, out of 102.00 decimal feet, we take our height of instrument and subtract that from our top of our footing form to get what we're going to be reading on our rod. We're going to take out our calculators and punch this in together. 104.58 minus 102. And we come up with a rod reading of 2.58 feet. This 2.58 decimal feet is what we would use as our rod reading to set the height of our footing form. This may seem overwhelming at first. That's okay. Once we practice this on the shop floor, this is all going to come together for you. This is an important component of layout. To conclude, layout is a critical component to successful construction. Local 27 carpenters use layout every single day on a job site. With a solid math foundation, coupled with in-shop practical application, you will be adding to your toolbox of skills and making union job sites more productive, ensuring future work for Local 27 and the UBC.